Good afternoon or good morning, everyone, and thank you for joining us. Today, we have the pleasure to welcome Professor Douwe van Hinsbergen from Utrecht University. And today he's going to talk to us about the plate tectonics future of East Africa. And Douwe, I leave you the floor.
Thank you very much. And thank you for this invitation. I had never expected to give a talk in Africa while it's freezing outside. So this I'm very honored for the opportunity to give you this talk. I just said I think it's a fantastic silver lining of the fact that we got used to Zoom meetings that I can now give talks all over the world just sitting behind my desk. I am going to talk about geology today, and if there is stuff that you really don't understand while I'm saying it, please raise a hand or so, otherwise I'll answer questions at the end. I will start with a brief introduction of who I am and what I do, and then I'll take you on a thought experiment through a geological future to learn something that we might use in the geological past and understanding the geology of East Africa. Okay, I'm at the heart a field geologist. I study rocks in the field. I study structure of rock units in the field, and I study paleomagnetism, a technique to use the magnetic field that is stored in rocks to make reconstructions of tectonic motions. And I do that in origins, so in mountain belts all over the world. And here's an example what we do with that information that we get from the field. So these are where's my mouse? There's my mouse. So these are, for instance, examples in Turkey where we have done structural geology, and we use the structural geology of those mountain belts to work out what the architecture of entire orogenic belts are that form at subduction plate boundaries. With here an example, for instance, in the Northwest Pacific. We make cross sections, work out the paleomagnetism, and then we make reconstructions of the nature of the lithosphere that existed in the geological past, and out of that we can make paleogeographic reconstructions. And those paleogeographic reconstructions, so this is what we think the world looked like in the Northwest Pacific about 60 million years ago. Those reconstructed plates are then included into a global model that we are making, and the global model we use for two different things. On the one hand, we can use this geological reconstruction to start to do geophysics of the Earth's mantle. For instance, we can combine the reconstructions of plates that were lost through the process of plate subduction and trace them back into the Earth's mantle with geophysical seismological techniques, where we can see in the mantle where those plates are, and then work out how plates sink through the mantle and learn about what drives plate tectonics and how the mantle underneath our feet is operating. And on the other hand, we can use those reconstructions and make reconstructions of paleogeography, so the reconstructions of the Earth's surface in the past, which is of importance if you want to study paleontology, paleobiology, or paleoclimate. And one of the examples, what I really like, is making web tools. So we try to translate the findings that we have in all those reconstructions, which are quite technical, of course, and we try to translate them to communities who have not studied or cannot study, will not study the details of our reconstructions. For instance, in a website that we have developed, paleolatitude.org, and this is a new version that will come out next summer, whereby you can, for instance, see here, if you click on Kigali, you can see what the paleolatitude of Kigali through time has been, right? It is now at the equator, but about 380 million years ago, we were close to the South Pole. And we can reconstruct what the temperature has been in Kigali in the last 80 million years. And if you then compare that to Scotland, you will see that the temperature rises on the temperature changes during climate change on the poles is much higher than on the equator. So these are applications of the work that I do. But in this talk, I will mostly concentrate on plate tectonics and orogenesis, using Africa as an example. And if we look at the geology of East Africa, then we have basically two end members or two stages in the famous Wilson cycle. The Wilson cycle is the cycle that was invented by, or that was for the first time conceptually came thought up by Douwe Wilson about 60 years ago, and in which he says the Earth's surface evolution is an endless cycle in which continents break up in rifts. Then the rifts develop into oceans. At some stage, the oceans start subducting and are lost, are recycled back into the mantle. The continents collide. We make enormous mountain belts. The mountain belts are then eroded, and then we have a continent that will break up, etc. Now, in East Africa, we have systems like that, and this is a conceptual cross-section of the famous East African origin that I will show you a map of in the next section. You are probably more familiar with that than I am, but in East Africa and Arabia and Madagascar, there is Antarctica, there is a large collision happened about 550 million years ago between continents, and an enormously complex mountain belt was formed that is now mostly eroded, that makes up now the crust of East Africa. And from the geological study of that crust, we tried to figure out what processes made that mountain belt. And eventually, if we go back to the very beginning, then we see that those processes that made that today's very complex geology were in principle pretty simple. Originally, these were rock units that were mostly sedimentary, piled up, and then all hell broke loose, and we ended up with the origin that we see today. And what I will be talking about today in this talk is how, out of that enormously complex origin that we see today, we can go back to the original situation and work out all the processes that happened to make that mountain belt. And these are the processes that involve the formation of ore deposits and that involve the formation of almost all economic deposits that we use today in society. So the famous collisional stage of the Wilson cycle that is, for instance, active today in the Himalaya and in Tibet occurred about 550 million years ago and made the East African origin. This is a picture of the supercontinent Pangaea about 300 million years ago. And then you see, or Gondwana, the southern part of Pangaea. And then we see that there are large cratons, continental blocks that are billions of years old in the west, including Kalahari Craton and the Congo Craton and some others, and in the east. And in between, there is this major mountain belt, and that mountain belt is now located there's Kigali, so just east of Kigali over Somalia and Arabia. On the other end, the stage on the opposite side of the whole Wilson cycle, we see today in the East African Rift that ends in the north in the triple junction with the Red Sea and the Gulf of Aden, two active spreading centers, and that continues both west and east of Kigali right now, as you, I'm sure, are well aware. So one of the things that, the angle that I'm going to take here is I'm not going to try to reconstruct the East African origin itself. I'm going to work out how we could conceptually do this and how we might help ourselves to interpret that infinitely complex origin by working out what different elements have to be added together to make mountain belts like that. And I'm going to do that with a thought experiment. About 4 years ago or so, we published a reconstruction, a detailed kinematic reconstruction of the Mediterranean region, and that was picked up by the media, and I got questions from journalists about it. And one of the questions that was repeatedly asked is, it's nice that you can reconstruct mountain belts, but can you also predict the future ones? And we thought, well, we can, but why would we? Because we have to wait 300 million years to see if we're right, and there, we can't. So what's the point? But then we thought a little bit harder, plus COVID came and we were all sitting inside and we couldn't study rocks in the field and there was little to do. So we decided, well, let's give it a shot. If we want to try and reconstruct mountains of the future, what would we have to do then? How can we do that? Because we can just draw a bunch of mountains, but is there a systematic way in which we can predict what origins, what large mountain belts of the geological future are going to look like? And we developed this around a course that I'm giving my master's students. And for that course, I wrote this paper that if you're interested, that I can send you to read with, which is basically the background of that whole project. So if we want to understand what the mountain belts of the future, what the origins of the future look like, we have to develop a couple of rules. What we have to do is we have to, in our minds, forward model tectonic processes by learning from these processes from the geological past. And we need a set of rules that explain how we can translate the modern geography into orogenic architecture through subduction zone processes, right? So this is a schematic map, tectonic map, a geographic map of the modern Indian Ocean between Somalia and India. Then we have to add a bunch of rules, and if we add those rules, then we're going to end up with a scenario for the future in which we have that mountain belt. And we might be able to see how sensitive initial choices are for the eventual origin or orogenic architecture. So the first step that we have to take is that we have to create new plate boundaries that don't exist yet today or that are about to form. And what we chose in this model is to start with the East African Rift, which is developing into a new plate boundary. It's going very slowly, right? The amount of motion on the rift is maybe some tens of kilometers. The total amount of rotation of the eastern plate of the rift, the Somali plate relative to Nubia, to the African plate, is, I think, 0.8 degree or so. It's not so much yet. But let's for the sake of argument, say that this plate boundary develops into a full ocean. The first question, which is it's a little sidestep, but one of the things that is interesting to figure out is, why do plate boundaries form in the first place? How do you form plate boundaries? Because the plate boundaries that we have today on Earth have existed typically for tens of millions of years, right? Plate boundaries are not features that form every day, right? So the basic rules of plate tectonics tell us that the Earth is divided in a dozen or so major plates, that each plate is surrounded on all sides by plate boundaries, divergent mid-ocean ridges, transcurrent are transform faults, and convergent are subduction zones. And those plate boundaries end in triple junctions, and those systems are active for tens of millions of years. So why do we form new ones? Well, one of the ideas and one of the observations, one of the ideas is that mantle plumes may assist the formation of plate boundaries, and particularly continental break. And one of the bases for that idea is the East African Rift, Red Sea, Gulf of Aden system, where at the triple junction there is volcanism, and there has been, particularly when the extension started, there has been the famous Afar Large Igneous Province, or the Ethiopian Large Igneous Province, major basalt outpourings of about 30 million years old that preceded or occurred early in the rifting history of the East African Rift, the Red Sea, and the Gulf of Aden. Now, from a petrological point of view, since the onset of the rifting and the magmatism is synchronous, it might be that the two conceptual solutions is that the magmatism caused the rifting, or the rifting caused the magmatism. I'm not a petrologist. I'm not going to go into the details of this particular example, but one of the things that is interesting is that almost all ocean basins that formed, that we have today, started opening after the emplacement of a so-called large igneous province. For instance, the Kerguelen large igneous province triggered or was associated with the breakup of India from Antarctica and Australia. The Karoo large igneous province that is known from particularly South Africa preceded the breakup of Madagascar from Africa. We have the Paranaia Tendeka in Brazil and in Namibia, the large igneous province that was associated with the opening of the South Atlantic. Morondava, around 92 million years ago, was associated with the breakup of Madagascar and India, and the Deccan Traps of India are associated with breakup of India from from the Seychelles. And what I depict here is a paleogeographic map. You just see the continents shifting around, but all of these features were associated with formations of new spreading ridges, rifts and spreading ridges, new plate boundaries. So is it possible that these large volcanic features help driving the formation of new plate boundaries? Well, from petrological and plate reconstruction, as well as geophysical observations of seismology, the idea is that these large igneous provinces are the result of large plumes that rise through the mantle, and that that rise through the mantle, and that as they reach the lithosphere, weaken the lithosphere, rise up the lithosphere, cause extension, and because plume heads may spread let's say like mushroom clouds, may spread below plates, they may actually push plates. So let's see if these things can help formation of plate boundaries. And in that context, it is interesting to see that this is something that we have been doing over the last 7 years or so, not 7 million, over the last 7 years or so. We have worked out the complete plate boundary that formed when India broke up from Madagascar. The India-Madagascar separation is quite easy to reconstruct because it formed an ocean basin, and that ocean basin is still existing today. However, that ocean basin that stops around the Amirante Ridge, which is west of the Seychelles, and from there on, most of the original plate boundary has been destroyed. But what we see in Amirante is that the plate boundary became compression. There is folding, there's thrusting. And then we can trace, if we reconstruct the entire plate boundary by reconstructing the mountain belts of the Eastern Mediterranean, of Northern Arabia, Oman, and Pakistan, Afghanistan. If we reconstruct that entire plate boundary, then we see that a subduction zone started forming below, above which prominent belts of ocean floor formed that we now find in Oman, for instance, as ophiolites. And this plate boundary was compressional. Now, this is also to be expected because if we reconstruct the Mascarene basin between Seychelles and Madagascar today, then we see that in the early opening history, around 19 million years ago, India was rotating relative to Africa, and that rotation is associated with contraction north of that pole. So is it possible that those mantle plumes, like we now have in Afar, aided the formation of that plate boundary? And to solve that, there are two puzzles that we had to solve, and we did that with numerical geophysical modeling. Well, I didn't do that, I'm not a geophysicist, but Bernhard Steinberger here in the bottom right, a very well-known geophysicist from Potsdam in Germany, he performed some modeling. There were two puzzles that we had to solve. The first puzzle is that the large igneous province, so the massive volcanism that is created when a conceptual mantle plume is rising to the base of the lithosphere, that generates enormous melting and the formation of these flood basaltic outpourings. Those outpourings, the flood basalts, in the case of Morondava, the breakup of India and Madagascar, were about 92 million years ago, whereas the initiation of rotation and the initiation of subduction from archaeological reconstructions was about 104. So there is about 10 or 12 million years in between the onset of the plate motion and the outpourings of the lavas. And one of the things that Bernhard showed about 10 years ago, 11 years ago now, is that if we model the rise of plumes below plates, there are two effects. The first effect is that plumes have to spread out below plates and can therefore push plates apart actively. And they may speed up that motion, they speed up plates by perhaps 1 or 2 centimeters per year, which is not dramatic, but it's enough to make a new plate boundary, because all we need is about maybe 100 kilometers of motion or so. And the second thing is that because when a plume rises, the mantle ahead of that plume has to get out of the way. So the effect of horizontal motion in the mantle because of plume rise ahead of a rising plume predates the arrival of the plume below the plate by 10 to 15 million years, which fits here the observation. The second thing that we had to show here in the case of India and Madagascar is that if we simply make a model in which we drive plate motion by the spreading out of mantle plumes below plates, then we can do that, but we will get a rotation pole between the two plates that is very far away from the plume head that is doing the trick. However, if we add continental keels below India and Africa, then we get something else, right? Continents are much thicker than oceanic plates. Continental crust is about 30-35 kilometers, and continental lithospheres are something like 150 or 200. Whereas in oceanic lithosphere is only 60 kilometers. So if continental keels exist in the mantle amidst regions with thinner lithosphere, you get that those plates are resisting motion through the mantle because of their keels. And those keels will start to act as pivots around which the plates will move relative to each other. And that drives the Euler pole from north to south in this case. And if you then start to push Africa and India apart, you will get contraction in the north. So in this special occasion, not only did the plume likely assist the formation of ridges, it even made subduction zones. And this is a cartoon made by Bernard's daughter, Alicia Steinberger, who's a science cartoonist, whereby you can see how that worked out back in the day. So the formation of a new ocean here is accompanied by the formation of a subduction zone there. There is no record that a subduction zone was formed when here at the IFR triple junction, a plume rose about 30 million years later. But I believe that not only will that plume have weakened pre-existing weakness zones inherited from much older geological history, it may have played an active role in driving the initial stages of divergence. Okay, so now that we have made a rift, how do we end up with a complex origin like this? And basically what we are then looking at is a sum of 5 features. We have extension and basin formation, and the basin formation accompanies the accumulation of sediments and volcanics, like is happening today in the East African Rift. We add contractional deformation, we add magmatism, we add metamorphism, and the metamorphism is simply the change of the sedimentary and magmatic rocks that exist in the origin, and their transition into new mineral phases and new mineral compositions because of changes in pressure and temperature. We add denudation, weathering and erosion, and if we add it all up, then we can make something that we see in East Africa today, the architecture of these complex origins. Now, in our thought experiment, where we start with the breakup of a plate and the consumption of an existing plate, we need to figure out how we can make orogenic belts out of the present-day geography that we see on Earth. And if we start to make orogenic belts, there are essentially two different ways of making this, 2 different components of every mountain belt. We have, on the one hand, we have so-called accretionary orogenesis. Accretionary orogenesis means the transfer of rock units from a subducting plate to an overriding plate. If I would have if your arm is a plate and you have a sleeve on your arm, your arm will subduct, but your sleeve will stay behind, and that folded up sleeve, that is an accretionary origin. So here we are in a downgoing plate that is moving below an overriding plate. In that downgoing plate, I can have oceanic lithosphere, but also continental lithosphere. And the top part of that downgoing plate, typically the sediments, and sometimes a little bit of the older basement underneath, or the magmatic basement underneath, that may accrete as big as thrust slices, thin thrust slices, at the front of the subduction zone and below the subduction zone, below the overriding plate, and form a so-called accretionary origin. Anything that was below the accreted rock units is lost by subduction in the mantle, right? Is subducted. So the vast majority of lithosphere that went into an accretionary fault thrust belt, into an accretionary origin, is gone, and you will never see back. It goes back into the mantle. And we can make accretionary origins and accretionary orogenesis in all different combinations of subduction. We can make it during ocean below ocean subduction, although that is very rare. In most cases where oceanic plates go down below oceans or below continents, there is little or even no accretionary orogenesis. If you take, for instance, the examples in the West Pacific or in the North Pacific, in the Aleutians, everything has gone down. Below the Andes, 10,000 kilometers of crust has disappeared and not a single rock has been left at the surface. But in other places like in Japan or in New Zealand, it is, or in the Matran, north of Oman, it is quite, there we have big accretionary prisms. If continents go down into a subduction zone, their upper crust will always accrete. I am not aware of any location on Earth where a continent must have existed that has disappeared without leaving a trace. And I've tried to reconstruct them. There are ways of doing that. But I've not been able to find any place where a continent must have disappeared and there's no record in the there's no geological record. The textbooks tell us that continents cannot subduct, which for continents the size of Africa or Arabia is probably correct. But if we take something like the Seychelles today in the Indian Ocean, these microcontinental slivers, or we take continental margins, they can actually go down. So thin continental crust can actually go down without too much trouble, although it will always leave behind these accretionary prisms, these accretionary origins like the Himalaya or the Zagros today. And if those origins go down, if those plates go down, they may they may off-scrape their sedimentary sequences, and those sedimentary sequences are very useful for us if we want to reconstruct what the Earth looked like in the past. Because those sequences are very predictable, they're almost always essentially the same, and we can use them to reconstruct what has subducted. If oceans subduct, then we find a relatively simple sequence that was worked out by Isozaki in 1990 in a beautiful paper. And Isozaki showed from the geology of Japan that every thrust slice in Japan, every major accreted thrust slice in Japan contains something that he called ocean plate stratigraphy, OPS. And from bottom to top, that consists of the top part of the magmatic basement of an oceanic plate, which are typically pillow basalts. On top of that, we get very deep marine open ocean sediments, so-called pelagic sediments. These are rained down little fossils. And because oceans are so deep that all carbonate dissolves that reaches the seafloor, only the siliceous little fossils, for instance, from radiolaria, are preserved. So we get thin layers that contain an enormous amount of time of typically red oozes that you find on the seafloor. And then as the plate starts to approach, here a trench, we get sediments that are dumped from the mountain belts in the overrunning plate into that trench. And those sediments are sandstones typically that are deposited as turbidites, so as mass transported sand avalanches into the deep sea. So we see a sequence of the top of the ocean floor, of radiolarian cherts, and then of foreign basin deposits. And these units you will find for all Phanerozoic subducted, if you accrete anything from a Phanerozoic ocean floor, it will have this sequence. And the age difference between the magmatic basement and the foreign basin deposit tells you something about the age of the oceanic crust at the time it was subducted. The geochemistry of those basalts will tell you whether you're looking at a piece of ocean floor that formed in a mid-ocean ridge or something like a hotspot volcano like we have today in Hawaii. For continents and continental margins, we get a similarly predictive sequence, although there can be more variation than in oceans. From bottom to top, you may find fragments of the original continental basement, depending on how deep the fault existed in the downgoing plate above which the rocks are treated. So we can have fragments of continental basement, let's say Pan-African or something like that. Then on top of that, we'll find finding upward clastic sequences and evaporites sometimes, and mafic magmatism that is associated with rifting. So this is the stuff that is today forming in the East African rift. In Rwanda, you have these big rift-related volcanoes that are pouring out lavas amidst terrestrial deposits and lake deposits. If we would continue with that, we're going to find hemipelagic sediments. So first marine clastic sediments, and then hemipelagic sediments, so just clays. And the farther we rift, the farther we get away from the sediment sources, and the farther the cooling of the rift system occurs, everything starts to subside. So all we get is clays, and then we will get pelagic limestones or carbonate reefs that we find on the passive margin, and like the reefs that you have offshore East Africa today. Then, as that system approaches a subduction zone, we get the same thing as in oceanic plates. We will get fallen basin plastics that are dumped onto the downgoing plate, and they mark the arrival of that system into a trench. And all origins are essentially built up of these two types of stratigraphy. And because the stratigraphies are very predictable, you can navigate yourself through the origin, and you can navigate yourself through paleogeography by simply looking at the stratigraphy. And the stratigraphy may be buried, of course, in a mountain belt and metamorphose. So what we here call a pelagic limestone may become a calc silicate or a marble, and the fallen basin deposits will become mica schists, and the magmatism that we see at the bottom may become orthomyces or amphibolites or stuff like that. But overall, the stratigraphy is still predictable, similar for the oceanic part. Overriding plates are a different beast altogether. Overriding plates can be extended to make back-arc basins, or they can be compressed to make plateaus, right? So we can make something like the Tibetan Plateau or the Andes, or we can make something like the Basin and Range Province in the Western United States, or we can make back-arc basins like we have around the Pacific. And these features can occur in any combination of oceanic or continental downgoing and overriding plates. There is, when thick continents like India start to underthrust other continents, then typically we get plateaus like in the Himalaya or in Iran. But a large part of the plateau in Tibet formed during oceanic subduction, and the Andes formed entirely during oceanic subduction. So you do not need continental collision to make upper plate origins and plateaus. Likewise, in the Western Pacific, the subducting plates are oceanic and many of the overriding plates are extensional. But in the Mediterranean region, the downgoing plates is mostly continental, and the overriding plates are still extensional back-arc basins. So there is no systematic relationship between the nature of the downgoing plate and the style of deformation in the overriding plate, which is something that we have to bear in mind when we start to predict mountains of the future. In the end, what is important to predict whether we find mountain belts whether we find extensional basins or intraplate origins in the overriding plate is simply the relative motion between the bend of the slab, the location where a slab is bending into the mantle, downgoing plate is bending into the mantle, and the overriding plate. Just from the top of your head, if I have a downgoing plate that is going into the mantle, but the location where it bends is stationary and my overriding plate is approaching, it will undergo friction and it will make a mountain belt. This is what happens in the Andes, for instance. If my overriding plate is retreating relative to a stationary slab bend, I get overriding plate extension. And if I have a stationary overriding plate and my slab bend is moving, I can make the same combination. And that is what determines the style of deformation in an overriding plate. And these two things, accretionary orogenesis and intraplate or upper plate deformation together make our large mountain belt. Now, I'm not going to go through all the details here of the rules of orogenesis that we made up. But the most important take-home message is here. Two guys sat together and we looked at the map of we looked at the geographic map today, and we started to think what would happen to this particular feature, for instance, a seamount, if we would stuff it into a subduction zone. Are we going to find anything back in the geological record or not? And we looked in a lot of different geological records of origins around the planet to see if we would find features like that. And some you do, right? If there is a microcontinent like the Seychelles today and we subduct it, will we find something like that in an origin? Yes, we do, because we find it all over the place. The Mediterranean is full of it. The Himalaya, there's many of these examples in Southeast Asia. If oceans disappear, will we always find a record? Well, no, but sometimes we do, etc. I think the most interesting thing that we realized is that I've been talking about the large igneous province that we have in Ethiopia and Afar and Djibouti, and just north of you guys. These features in continental domains go back billions of years. But in oceanic domains, they also exist, right? This is thought to be mostly igneous rock. Also south of Madagascar, there's a large igneous province on the ocean that is related to the Morondava plume. And for instance, the Ontong-Java Plateau in the Western Pacific is a region the size of Madagascar with 20-kilometer thick basaltic crust because of a large igneous province that formed. Whereas in accretionary origins, we almost never find relics of large igneous provinces. So these things must have existed also in oceans billions of years ago, but they subduct without leaving much of a trace, probably because they're very strong. So the overriding plates may be tormented while they go down into a trench, but you will hardly ever find them. So with our 10 rules, we're going to see now what happens to the Indian Ocean if we start to subduct the Indian plate, and if we start to make an ocean out of the East African Rift. And we do that with a few boundary conditions. First of all, we need a plate model for the future. And this lady, Hannah Davies, who was a PhD student in Lisbon, has published a paper a couple of years ago in which she built future supercontinents for thought experiments to see what that would do for climate. One of her scenarios we took, which is this scenario here, whereby the Somali plate will break out of the rest of Africa and open an East African Ocean. And while that East African Ocean is opening, Somalia will move towards India. And in Hannah's reconstruction or Hannah's construction, that was simply paleogeography and continental drift. So she just let that ocean disappear. But we have to do that now by subduction. And then we're going to predict the overriding plate and the accretionary origins. And to stay completely on par, we describe the construction as if it geologically happened. And then you need also a time scale. So to be complete, we also invented a time scale of the future, which was mostly fun and not so much science. And we named the periods after languages surrounding the Indian Ocean. So we have made two scenarios, and the only difference between the scenarios in initial condition is the location where we start subduction. I showed you before that we've been doing a lot of work on how to reconstruct mountain belts and how to reconstruct plate boundaries at the moment of their formation, subduction zones. And we know that subduction zones can form at mid-ocean ridges or at continental margins. So in one scenario, we started the subduction within at the mid-ocean ridge between India and the Somali plate. And in the other case, I think we made the subduction zone along the Indian margin. So this is the first scenario in which we invent a subduction zone that is northeast dipping below the Indian ridge. And the first thing that we and then we see what happens if that occurs. Well, if we have intraoceanic subduction, then the leading edge of that oceanic plate is going to be placed at some stage on the East African margin, and we'll make an ophiolite. In the overriding plate, we can reactivate that ridge, and we can make supra-subduction zone ophiolites. Doesn't really matter. And the first thing that will happen in about 50 million years into the future is that we get a mountain belt that is located along the margin of East Africa, and then make this. It will follow the trend between, and it will follow the bend in the Comoros region around Madagascar, and it place ophiolites on both sides of Madagascar. At that stage, our subduction zone is dead because we believe that the Somali continent is way too thick to disappear into the mantle. So we have to do something to our subduction zone. And one of the things that typically happens in these locations, like today on Kamchatka, is that the subduction zone polarity changes from east to west. And now we start to subduct the remainder of the Indian Ocean below that subduction zone. Below the East African margin. And then eventually, so we subducted ocean, and eventually the Indian plate margin will come to that origin. And we create here a large mountain belt that, to stay on par with the Himalaya here, we call this Somalaya. Behind that, we get a major ocean that is opening around the pivot pole here near the Macron, and that causes the so-called intra-African Ocean, or the East African Ocean, and Kigali is located somewhere there or so will be part of the Indo-Eurasian plate at that stage, 200 million years in the future. Interestingly, if we would start the subduction zone at the East Indian margin here, we get a completely different origin. The geography is the same, but the plate tectonic history will be totally different. The first thing is that if we have that subduction zone here and we apply the motions in the model of Hanna, we have to break India in two. And like happens with the East African Rift, today we have chosen to do that along existing weakness zones in the Indian Craton. I mean, you can take anything you like, but this is a logical place to do that. So we break India in two. And now, instead of making ophiolites, we will not make ophiolites. We immediately go into a continental collision scenario, but that scenario is not 200 million years in the future, but only 50. And then if we want to move on, we have to close that back arc ocean that we formed, and eventually get an origin that looks entirely different from the origin in the previous example. And we can make a little comparison. An origin, the Somalaya origin in the first example, is pretty simple. We have an older part of a mountain belt that is thrusting ophiolite and accreted rocks over the, in this case, the Somali plateau that we invented. And then it is followed, we have a suture zone here, and then it is followed by an accretionary origin that is opposite facing and that is thrusting over India, mostly made out of the Indian continental margin. Origins like this are very common. We find them in many places in the world. If we, and this is 200 million years in the future, in a Mumbai origin scenario, we do not have the polarity switch, but we suddenly have to invent, this cross section goes here. We get two different sutures. We have breakup of the Indian continent in two, and we get totally different orogenic architecture. And what they show you is that eventually the formation of a mountain belt is dictated by the initial plate configuration, the initial subduction zone configuration, and the paleogeography. But paleogeography alone, or initial subduction configuration alone, can make will not do the trick. So you have to take both of these things into account. But the structure of the origin will tell you what happened. Okay, so accompanying this thought experiment, we made a little movie for a movie clip is about 2 minutes for public outreach purposes, and I'm going to show you that now just to show your students or to show anybody who might be interested. This is that little movie. It is intended to reach a wide audience. It also did, particularly in India. It became quite popular in the media. So I'll shut up now and show you that little clip.
Geologists at Utrecht University offer a glimpse of the distant future. These are the Somalaya Mountains, the largest mountain range you will never see. Because the Somalaya Mountains don't exist yet, but will form in the next 200 million years.
Okay, I have to show you that again. This is only the teaser. Okay, I'll come back to this. I have to. I'll show you that movie after I finish the. Stupid me! I never checked. I'll show you that after I finish the talk, which is in 2 slides from now. Great. So just to wrap it up. If we now want to study, how can we use this thought experiment? If we take a real mountain belt today, and I come back to the East African origin, then we can look in the geological record and we see that particularly in the Arabian side, we see large complexes that are derived from oceanic systems, whereas in East Africa and in Rwanda, we see parts that are mostly continent derived. And we can use the conceptual combinations of plates here, but particularly if we turn them around, perhaps to start deciphering the entire evolution history of this origin, whereby the continent-continent collision and the continental subduction side may most apply to the southern part here in Africa, whereas the intraoceanic and ocean-continent side may apply more to the northern side in Northeast Africa and in Arabia. So that is what I had to tell you, but I will now switch quickly to my internet. Let's see how I stop this and show you the proper movie instead of only the teaser, because that is highly frustrating to only show that. Can you still see my screen?
Yes.
Okay. That is to say, I'm now showing you YouTube. Otherwise, you don't know what you're looking at. Okay, this is the real one.
For million years. Let's go back in time first. The Earth as we know it today looked very different in the geological past. Millions of years ago, the supercontinent Pangaea broke up into several tectonic plates. These plates started to move along plate boundaries. At so-called subduction zones, one plate moves below another. The upper plate can get squeezed together, and the rocks of the lower plate can be scraped off, creating massive mountain ranges all over the world. It is a never-ending process. Using data from present mountain belts, the Utrecht geologists have now deduced some rules of mountain building. Using these rules and a model of future continental movement, they can predict how subduction will transform the present-day geography into mountain belts in a future that lies immeasurably far away, where Somalia will break away from Africa and drift towards India during the next 200 million years, forming the Somalaya Mountains in the process. By applying these mountain formation rules, we can better interpret Earth's paleogeography. This is important to study processes of the geological past.
Okay. Well, okay, thank you very much. That is what I that's what I had to tell you. And if there are any questions, I'm happy to take it.
Yeah, well, thank you very much, Douwe, for your presentation. It was really interesting. So we have time for question as usual. So everyone would like to ask a question can unmute himself or herself and ask a question. Ali?
Yes, thanks, Van, for your very nice presentation. You hear me well, right?
Yes, I do.
Yeah, thank you. It was very clear, but I have a couple of questions. I will just start with one question just to let others ask, and then if we have time, I can continue. For my first question, I'm very interested in studying grafting and the rule of mantle plumes. So if we believe, as you mentioned, that the mantle plumes are the main trigger for the rift and other following plate boundaries, let's say. So my very simple question, what would be the main reason for the mantle plume concentration or formation? So for instance, in the upper region, okay? And the second part of my question, what would be the evidence for the present day existence of mantle plumes or past? Is it just the flat basalts or this huge volcanic provinces that are evidence for mantle plume, or there are some geophysical exploration tools that can provide us with evidences for either past or present day mantle plumes? Yeah, that's my first.
Okay, so you asked two questions. The first was what may drive their formation, and the second one is there evidence today apart from the magmatic?
Exactly.
I'll start with answering the second one because I think it's better to start with observation and then come with all sorts of speculations what may drive it.
Yeah.
The evidence for mantle plumes. Okay, the evidence for. I think the main question is the evidence for mantle plumes coming from the very deep mantle, because that is the interpretation that we have. There is, let's say that the evidence that plumes exist is, first of all, there are long-lived, the first piece of evidence is time. Many of the large igneous provinces are the beginning of a very long period of magmatism that may last 150 million years or so. For instance, the Hawaii Emperor Bend is a more or less mantle stationary source of magma that has existed for the last 85 million years. The Morondava large igneous province led to a hotspot tract that is the Marian hotspot that is still active today and that has been existing for 92 million years. And it's hard to imagine. So one of the things is that there must be this long-lived source of magmatism in a more or less mantle stationary position. The second part is that it must come from deep, comes from two lines of evidence. The first is geochemistry. There are, in many of these mantle plumes, there is evidence that pieces of mantle are involved that have existed, that are essentially original from the accretion of the earth or the very early segregation of the earth. Mm-hmm. So there are, for instance, many of these lavas have helium isotopes, helium-4 isotopes that are so light that if they come into the atmosphere, they immediately escape to outer space. So these must have been preserved within the Earth for the last 4.5 billion years, and it's hard to imagine that occurs in the upper mantle that is heavily involved in plate tectonics. So that is thought to be much better mixed. So that is one of the arguments from the geochemistry that this must come from very deep. And geophysical evidence from seismology shows in many places, such as in Hawaii, but also I think for the case of East Africa, that there are these, and for Galapagos, there was a recent paper, that these modern hotspots are underlain by deep-sourced conduits that go all the way to the core mantle boundary. What has particularly convinced me, and this is also the bridge to the first question that you asked, is paleogeographic patterns where large igneous provinces and hotspots and other features like kimberlites that are also thought to be linked to plume volcanism, where they come from. And what we see is that 95% or so of kimberlites, hotspots, or large igneous provinces are originated from a more or less circular zone around Africa, around modern Africa, and in the Pacific that correspond to structures that are located on the core mantle boundary. You can look it up if you haven't studied this before, but these are called large low shear wave velocity provinces. There are two structures on the core mantle boundary, more or less antipodal, below Africa and the Pacific. And all the plume-related volcanics plots, if you reconstructed, on the edges of these large igneous provinces. And the idea is then that deep mantle flow, which is probably very, very slow. But let's say if a slab reaches the core mantle boundary, a subducting slab approaches the core mantle boundary, material at the core mantle boundary has to go out of the way. And if it hits the edges of the LSVPs, it goes up, it is heated from below, and you get plumes that leave to the surface. And that is the current explanation for it that I believe is quite elegant. Now, that doesn't mean that every piece of intraplate magnetism is always plume related, but I know that this is debated by petrologists and geochemists for afar. I'm not sure whether every piece of geochemical infrastructure there can be explained by a plume, but I think that the plume model works overall quite well for that region.
Okay, thank you.
Yeah, Karim, go ahead.
Oh, thank you very much. That was really an exciting talk. That's quite interesting. So I remember many years ago, I heard about giant dike swarms in Mars and Venus, and where, I mean, these are two basically planets where we think that there is no geological evidence of plate tectonics. Then how would you reconcile those ones with what you're observing on Earth? I mean, are you alluding that they may be symptoms of different evolutions, or?
I'm not a specialist. My wife is a planetary scientist, so I should ask her. But I have no strong opinions about what happens on Venus and Mars. But what I do know that people have argued for, those dike swarms, as if I remember correctly, those dike swarms are radial around a center, yes. And that is one of the features that is commonly observed with mantle plumes on Earth. That you have these, and like Camp and other places, you have these big dike swarms that are pointing towards the plume source. And this is one of the reasons. So the idea is that this is mantle plume related. Now, mantle plumes, I believe on Earth are probably linked or are influenced by the plate tectonic cycle. But you do not need, and this is something that Valérie Maupin, for instance, has shown, you do not need to have plate tectonics to make plumes. This is basically something, if you have a viscous substance that you heat from below, you get these features. Basically, a lava lamp does it, okay? So this is one of the reasons why I thought it was interesting that you could possibly make not only ridges, but also subduction zones by plumes, because plumes in that way may have played a role in the formation of tectonic plates in the first place. So that is one of the thought experiments we had. So as far as I know, what we see on Mars and Venus cannot be explained by plate tectonics, but perhaps one form or another of plume magnetism may help there.
Okay, thanks. Thank you.
Valentine.
Thank you very much for this very interesting talk. I was really interested because I submitted last week a paper. I'm studying the EAIFR depression, and I tried to do a bit of what could come in the future. And I guessed that the East African rift system, because it's not driven by a subduction, would rather do a failed rift, and that the Red Sea might continue for a moment, not getting to a big ocean, because of course we're in the collision at large scale. So I was wondering whether you just assumed that rifting would continue and that subduction would initiate, or is there any modeling behind?
No, there's no modeling behind. I chose because I did not. What I wanted is a plate model, a kinematic plate model that I did not make up myself, whereby somebody would just do it. And I wanted to take that model and see what the consequences were, because if I would have made that myself, then I'm starting to tweak it to make it the way I wanted. Now, Hannah made 4 models, and she didn't care about plate tectonics there. She just wanted to see what different supercontinent configurations would do. So she just took it and ran it. And she decided that also without dynamic reasoning, that the East African rift is going to be a full ocean. And if you do that, then you need to get rid of the Indian Ocean, and that is what I wanted. So I agree with you that in the current circumstances, with the only thing that could drive ongoing opening would be ongoing subduction below Sumatra. But that ongoing subduction below Sumatra would then have to break the Indian plate so that you form a subduction zone on the Indian margin, etc. Now that is actually happening. Some people argue there's this intraplate deformation in the Indian Ocean. So I had enough excuses to do this, but your prediction is just as valid as mine. And we will probably both be long dead before we can test it.
Yeah, sure. That's the nice things. We can never be proven wrong.
Precisely.
And I don't know if there is time for a second question.
Yes, you do.
Yeah, for your model where you have subduction below India, then you modeled, you predicted an opening in the present-day Himalaya. Why would it open there, this basin, and not just drag Somalia directly by the subduction?
Oh, the reason that we got there, so we opened it not by breaking up the Himalaya, but by breaking rifts within India that are
okay. Yeah.
What we did here is we assumed that the subduction zones that form are mantle stationary. And Hannah prescribes plate motions in absolute plate motion context. So in her model, Eurasia is moving to the northeast. And if I make a mantle stationary subduction zone that I do not let advance, then I need to extend my overlap plate, and then I chose that rift.
Okay, yeah.
And so that's how it ended up. That is also why in the other scenario we get supra-subduction zone extension. So we limit the amount of rollback here. Otherwise, otherwise you can do whatever you want. So this is what we chose. Okay,
thank you very much.
Which I think, by the way, is not very realistic because subduction zones do have a tendency to roll back. But
yes, I do. I think 70%,
thank you.
I think. Are there other questions? Ali would like to ask us another question.
Yes, thanks again for your answers. And since we have time, I can ask one question. You have proposed these two scenarios. So my question is very simple. Which scenario would you think would be over the other one, or which scenario might be with high possibilities, taking into consideration the present day plate tectonic configuration and also the Red Sea, Gulf of Aden tectonism? You got my question, right?
In terms of subduction configuration, I don't think there is a preference. Both are just as likely. The main reason why I think that the answer is, eventually the Indian Ocean will presumably subduct. And what does that? In the current setup of how plates move, it is not likely that this is going to happen, but if Africa suddenly changes motion, it can happen. So I don't think there is a larger likelihood for one scenario or the other, and there is an equal, for instance, the subduction polarity at a ridge, we chose to let it subduct north. If we let it subduct south, we get something else entirely again. What I wanted to show with this experiment is basically that we can make a little playground to see what kind of structures we end up with. I showed you in this scenario here. So you see the construction of the Somalia, right?
Yeah.
Here you see this funny kink of ophiolites that are draping around this microcontinent of Madagascar. Okay. Yeah. Whereby we have ophiolites that are oppositely dipping. These ones abduct to the west and to the east and to the west. This is something that I reconstructed from Turkey in the Cretaceous. And I thought, this is really strange. How would that work? And simply by making it here, I showed that I figured out that with a simple subduction configuration and a relatively simple paleogeography with such an embayment, you can make these features. The Banda arc today is something similar like this. Okay, that doesn't continue as an ocean, but that is also an embayment like that. So I just wanted to see features that resemble today and how they may form. Another example here is because we have this funny irregular passive margin that is going to collide with India. All of our textbooks tell us that passive margins are parallel and then collide. Why is that? Because we take the Himalaya as example, and that's how we reconstruct the Himalaya. Even there I'm questioning that, but so This is an actual scenario that may actually occur. And if it can occur in the future, it can have occurred in the past. And one of the things that happens here is that this continent overrides India. Then here we have ongoing subduction that is rotating the continent. And that continent that here is thrusted over India is here pulled back. And this is something that is conceptually known as the process of eduction, where something goes down and then comes back up. And this is what we constructed, for instance, or speculated for southern Norway, where we see all sorts of features that explain well this way, but we never had a way of imagining how that would plate tectonically work. And suddenly here you see something that is totally made up, but it works according to plate tectonics, and it may have happened in the past. So I'm not so worried, I'm not so concerned about whether this is realistic or not as an actual future scenario. As a playground to see what may have happened in the past, I found it useful.
Okay, thank you.
If I may, I'll ask just a very quick question. The initial conditions where you set up the subduction zone, either in the middle of the Indian Ocean or at the extremity, was there any rationale behind it, or just the fact that the Indian Ocean would develop a subduction at some stage and somewhere?
Well, in the model of HANA, Somalia and India are going to converge, so I need a subduction zone.
Yeah.
And if a subduction zone forms, then the locations where we have reconstructed the initiation of subduction is along continental margins, or here large igneous province margin that I chose, or mid-ocean ridges or transforms. Well, we have no transforms in the right orientations here.
Yeah.
So we decided to take the ridge or the passive margin. You could also have taken this passive margin. You can make the subduction zone along this margin and have Madagascar collide with it. So, but I'm not aware of subduction zones that formed as by breaking an old piece of plate, not along pre-existing weakness zones. So that is why we chose these.
Okay, okay. So they were the weakness zone. Okay, thank you.
They're the weakest.
Yeah. Okay. Any other question, or should we close it? Well, I think we'll close. I would like to thank you very much, Douwe, for your presentation. It was very good. And I would like also to thank everyone who was there. It was very good. And wish you also a very good Christmas break, because I think this is fast approaching. And we'll close this 2002 series today. And see you next year.
Thank you all for your attention. If you have any questions, feel free to email and I'll respond soon.
Okay. Thank you.
Bye.